So this is my ender 3, and I only have one z-axis lead screw. So recently I had this idea that I'm going to upgrade it to a dual Z setup, but I'm not going to add a motor like a lot of other people do. I decide to have a parallel structure, which the other Z-axis is going to be held up by another lead screw that's not driven by a motor, but driven by a belt that is connected to the original lead screw. So to do that, you'll need the belts, and to tension the belts, you need some tensioners. So because I'm lazy and I don't want to build it myself, plus that there's already other people doing this thing, so I went on Google and did some search, and apparently there are lots of tensioners. So there's one thing in common for all of them. The tensioners are either placed in the center of the top beam, around here, or it's almost at the center. So I had this question: does it really matters for where you put the tensioner? Can you just put it on one side of it, or maybe you could put it like, what is the reason for putting it in the exact middle? What's the rationale? And so I sat down and did some math. So there you have it. Assume that this is the top view. This is the Y beam, the aluminum profile, and here's the lead screw. Here's another one. Here is the idler pulley that is going this way so that the belt is properly tensioned. And let's simplify this, and it could be like two triangles. And let's assume that this is constant B, this is constant A, which is this height. So constant means that just a number, it's not going to change because, well, your printer is just built that way. And X is the distance of the idler pulley to the lead screw on the left. So it is this distance. So we could use Pythagoras theorem, if I'm pronouncing that correctly, so that we could say that this side, it is a square plus x square and then square root. And this side, it is, well, you know that because the total length is b and this is x, this is b minus x. So that part, it's b minus x squared plus a squared. And if we plus those two together, it's the total length from here to here, or here to here. We're neglecting this because it always don't change. And so let's proceed. Originally, if it's not tension, the belt is supposed to be this length, which is B. So then we could construct a formula which, so the difference from the original, because it's difference, we're taking absolute value and we don't need to take it because this part is obviously larger than this. So we just write this again. I'm reversing it for clarity. So essentially it's this. And that is the equation we could get to model the difference between the new belt pass and the old belt pass. So right now I've just put this equation into the computer, and now you'll see that this is exact same equation. I just added a y over here. It doesn't really matter if you remove it, it's still the same. And a and b are still constants. I just gave them values this time just for simulation, you could say. And so b is 10, a is 1. So let's just remind you that b is the beam, like the total belt length horizontally, and then A is the distance where the idler could go like away from the beam. And so you see that this curve, it's like almost flat in the center, and then it goes up rather quickly on the two sides. So I just zoom in to the left part, and it's still the same curve, but I added some points, some lines that we have some points now. So when x equals to 0.5, the y value, which is essentially the difference, it's 0.67. And when x is 2, it's 0.29. By the way, this unit there's no unit in this case. It doesn't really matter because you could use millimeters or meters or whatever depending on your machine size. But yeah, that like just a ratio you could say for right now. And when x is 3, y is 0.23. And so when it's 0.5, it's almost 3 times the value at 3. So what we get here is that when the idler is really close to the lead screw on the left or on the right, it actually, like even if the distance the idler moves away from the beam, it's the same as we see that A, it's always 1. I never change it. The distance that the belt compresses is actually increasing. Wait, not compresses, but like the distance that you could pull the belt. So essentially that it becomes more and more effective because it's like the same space, but you could have longer belt length if the idler is closer to the lead screws. So apparently, yeah, probably the designers of those tensioners doesn't really think about where they should put that idler at. But it actually still makes sense to put it in the middle because that maximizes the contact area between the belt and the gears. But the problem is still, why don't you just invest more money, buy 2 more idlers, and then with those all 3 pulleys, you could construct something way better. And it actually doesn't matter for where you put the tensioning system, just like this one. Or reversely, if you want to save some money, you could just use 2 idlers and use the design from Handler, if I'm pronouncing correctly. And this creator is also famous for his mock-up of the Creality K1 3D printer, which Creality never open source, but he open sourced it for us. So yeah, I know there's some really mathy stuff in this, and if you just think about it and not write down the equation, you might just think, well, it's pretty intuitive that it's essentially linear because, well, look, it's just almost flat. But when we do the math, it's different. Then, well, probably next time when you design your tensioners on your 3D printers, it's just better to invest more money on more wheels and not put your tensioner in the exact center of your 3D printer's frame.